In lesson 10.8, we're going to be talking about systems of second degree equations and inequalities. So if you think about what a system of equations is, in the past we've been graphing maybe two lines at the same time and looking for their point of intersection. Well, systems of second degree equations are going to be similar to that, but they're going to be equations not just for lines, but for other things like parabolas, circles, ellipses, and hyperbolas. So sometimes our system might include a line and a conic section. A conic would be a circle, an ellipse, a parabola, or a hyperbola. In that case, there could be 0, 1, or 2 solutions. So if you think about what that could look like, this line and this circle never intersect, so there's no solutions. Here we've got a parabola and a line, and you can see there's one point of intersection, so that means there's one solution. And here we've got a line intersecting a hyperbola in two different places, and that would give us two solutions. We could also have a system that has two conic sections. In that case, there's a lot of different things that could happen. So we could get no solutions. Here's a parabola and a circle that have no points of intersection. Here is a circle and ellipse with exactly one intersection, so there's one solution. Here are two circles with two solutions. Here we've got a parabola and a circle, and you can see there are three solutions. And here we've got an ellipse intersecting a hyperbola in four different places, so there are four solutions. So we're going to talk about how to find those solutions when you've got systems like this. So first, in this example, we're going to graph the system. So we've got these two equations we're going to graph, and we're going to use the graph to find some approximate solutions first. Then we're going to solve the system algebraically and get exact answers for the solutions. So, starting with the graph. This equation right here is the equation of a ellipse. However, it is in general form. So the first thing I'm going to do is I'm going to change this to standard form. And the way I'm going to do that is by simply dividing by 36. Because when I divide by 36, you can see I get x squared over 36 plus 4y squared over 36 simplifies to y squared over 9. And then here 36 divided by 36 is 1. And now you can see that I've got an ellipse here that's centered at, well, this tells you it's centered at 0, 0. So, center 0, 0. This 36 tells me in the x direction it needs to be stretched by the square root of 36, which is 6 units. So 6 units to the right of the center, 6 units to the left of the center. And this 9 here tells me in the y direction, square root of 9 is 3, so I go 3 units above the center and 3 units below the center. And now I've got the 4 vertices of my ellipse, and I can use those 4 points to draw my ellipse. So it's going to look something like that. Next, I need to draw this graph as well on the same grid, and that is the graph of a parabola, because you can see that I've got an x that's squared, but there's no y squared. So that's going to be a parabola. But I'm going to want to get this into standard form as well. And the way I'm going to do that is I'm just going to factor out a -1 from y. And when I factor out a -1, that changes the sign of that plus 3, and I get the following. So that tells me this vertex of this parabola is, well, this would tell me the x-coordinate 0, and here the y-coordinate's 3. So this parabola has a vertex at 0, 3. Now that point happens to be one of the vertices of my ellipse as well. Now, from this vertex, I need to decide which way my parabola is going to open. Is it going to open up? Is it going to open down? Is it going to open to the left? Or is it going to open to the right? So to determine that, I look at my equation here. Since x is squared and not y, that means it's either going to open up or down. To decide whether it opens up or down, I look at this number here. Since it's negative, it tells me it opens down. So I know my parabola will look something like that. However, I'm not sure exactly how wide to draw. To find out how wide to draw my parabola, I need to find a few more points. So I need to find some values that satisfy this equation for x and y. So to find those points, I can plug in anything I want. So there are some choices that are better than others. Plugging in a 1 for x works pretty well. When you plug in a 1 for x, you plug in a 1 there, 1 squared is 1, and then solve for y. So I'm going to divide by -1 and then add 3 to solve for y. And when I do that, I get y equals 2. That tells me the point 1, comma 2 is also on this parabola. I will probably need some few more points, so I plug in a 2. 2 squared gives me 4, divide that by -1 and add 3, and I get that y equals -1. So 2, -1 is on my parabola. And then I'm going to plug in a 3. 3 squared is 9, I divide that by -1 and add 3, and I get y is -6. 3, -6 is also on my parabola. Now that gives me a good idea of what the right half looks like. Using symmetry and the fact that this is the vertex, I flip those across this line of symmetry here, and I get a point at -1, 2, -2, -1, and -3, -6. And now I got a lot of points, and I can just draw my parabola, so it goes through all of those points. Then, find the approximate solutions. Well, I'm looking for all the places where these two graphs intersect. That point right there would be 0, 3. And then there's another solution right there, and another one right there. Now you can see these two, I'm not exactly sure what points they're at, so I'm going to try to just approximate where they are. So this has an x value somewhere around 2.5, and the y value is not quite -3, but more than -2. It's about -2.8 or so. And then this point is about -2.5 for an x value and about -2.8 for a y value. And again, those are approximate solutions for this system of equations. So that's part A. Part A was to graph the system and find approximate solutions. Now I need to do part B, which is to solve the system algebraically, because I want to actually find exact solutions to this system. So if you remember back to when we were solving systems of linear equations, my two methods I tend to use to solve systems are substitution and elimination. And that's exactly what I'm going to do here with this system. So I'm going to start with my original two equations, which are x squared equals -y plus 3, and I've got x squared plus 4y squared equals 36. And now the substitution I'm going to do is already set up for me. This equation is already solved for x squared, so I know x squared equals that. Well, there's an x squared right there, so I'm going to plug this in place of x squared. And when I do that, I get -y plus 3 plus 4y squared equals 36. And now I have an equation with just y's in it. And now I'm going to solve this for y. So, to solve this for y, since I've got a y squared, I know this is a quadratic, so I'm going to get everything over to one side. Subtract 36, I get -33 equals 0. And now to solve this quadratic, I can either use factoring, completing the square, or the quadratic formula. This is factorable. It might take a little bit of work to figure it out, though. So, 4y squared will be y times 4y, and -33 will be 3 and 11. And then this needs to be negative, and that needs to be positive. Now that I factored it, I can do y minus 3 equals 0. That gives me one solution, and then 4y plus 11 equals 0 is going to give me another solution. So over here I've got y equals 3, and over here I've got 4y equals -11, so y equals -11 fourths. And there are my two solutions for y. However, I'm not done solving the system until I also have my solutions for x. And to find those solutions for x, I take my values for y that I got and I plug them into one of my original equations. So I'm going to plug them in to this equation right here. So I plug a 3 in and I get x squared equals -3 plus 3. Well, -3 plus 3 is 0, so I get x equals 0. That means when my y value is 3, my x value will be 0, which tells me the point 0.03 is a solution to this system. And that matches perfectly with what we got in our graph. There's that solution right there. Now, let's see what I get for x when I have a y value of -11/4. You might prefer decimal, in which case you'd be plugging in a -2.75. So I'm going to use the same equation, and I'm going to plug that in place of y. Be careful with your negatives here. It's -2.75 plus 3, which is the same as positive 2.75 plus 3. So I get x squared equals 5.75. Now the problem is, if you try to do the square root of 5.75, you will not get a very nice number. Square root of 5.75, and you can see it's not a nice whole number. So in order to simplify that correctly, I'm actually going to put it back into a fraction, and then I do the square root of 23/4. Don't forget your plus or minus, which is the square root of 23 over the square root of 4. So that's plus or minus the square root of 23 over 2. So that tells me when my y value is -11/4, my x value will be plus or minus the square root of 23 over 2, which means square root 23 over 2, comma, -11/4 is a solution to this system, as is negative square root 23 over 2, comma, -11/4. So here are my 3 solutions to this system of equations. And I can check these last 2 as well, because we did graph this to get approximate solutions, so let's see if our graph agrees with these solutions. Square root of 23 over 2, square root of 23 divided by 2 is approximately 2.4 or so, and then -11/4 was about -2.75. So let's look back at my graph. And right here, that is about 2.4, and that is about -2.75. So we got pretty close with our approximations there to the exact solutions that our algebraic method gave us.